What if I told you that the forces that govern our economy, all the booms and busts, the market swings, aren't just about human emotion? What if they followed the same physical laws as a bouncing spring or a speeding car? That's the idea we're jumping into today. So let me ask you something to get us started. What on earth could a car's suspension system possibly have in common with the financial futures market? I mean, one is all about metal and shocks, the other is finance and contracts. On the surface, it seems like absolutely nothing, but the answer is pretty surprising. Believe it or not, they both operate according to the exact same fundamental laws of motion. And that's the wild idea behind what we're going to call economic engineering. It's this framework that says maybe, just maybe, market behavior isn't just about messy human psychology, but also about the clean, predictable physics of the system itself. All right, so let's get into the weeds here. How do you actually translate the world of physics and engineering into the language of economics? Well, it all starts with this kind of translation dictionary. And honestly, the parallels are incredibly intuitive once you see them. In physics, mass has inertia. It wants to keep moving. In economics, demand has momentum. A spring in engineering stores and releases energy, right? Well, that's exactly what inventory does with goods. And a damper, or a resistor, that creates friction, which is a perfect stand-in for transaction costs in any market. Okay, so let's put this into practice. We're going to build the most basic system you can possibly imagine to see how this works. We'll start with what's called a first-order system. Just picture a buyer, a demander who's connected to a market. That's it. We've got our demand, which is our mass, and we've got an intermediary who creates some friction. Those are our transaction costs, our damper. But notice what's missing. There's no storage. There's no inventory. There is no spring in this system yet. Now, in a simple system like this, a price change doesn't just instantly snap to a new equilibrium. It kind of decays over time, like how the vibration from a plucked guitar string eventually fades to nothing. And the speed of that decay is what economists call the discount factor. The really cool thing is that mathematically, it's just a solution to a pretty simple first-order differential equation. Now, this idea really pushes back against a central tenet of classical economics. The traditional view is that markets adjust instantly. They have to, otherwise you could make risk-free money through arbitrage. But that whole view totally ignores reality. It ignores friction, transaction costs. You can't actually complete that arbitrage trade for free or in zero time. So the system has to take time to adjust. It's a physical necessity. And this is where the model gets really powerful. It gives us a real, honest-to-goodness mathematical formula for a famous idea from John Maynard Keynes, price rigidity. Keynes observed that prices seem sticky, that they don't adjust instantly. With this model, we can see that delay isn't some weird market failure. It's a predictable, physical property of the system. Okay, so that's our simple system, right? No inventory. But what happens when we add it back in? Because this is where things get really interesting. By adding just this one element, we get behavior that is so much more complex and, frankly, so much more like the real world. The moment we add inventory, our spring, to the model, it evolves. It becomes a second-order system. And it's that spring, that ability to store goods and then release them later, that gives the system the power to oscillate. It can overshoot its target and then swing back, creating the kind of trade cycles we see all the time. And how the system responds to a shock all depends on the balance between that friction and the inventory. Let's go back to the car. An underdamped system is like a race car suspension. It's super stiff, it reacts incredibly fast, but it might bounce you around and overshoot the mark. In a market, that's when prices just rocket past their equilibrium before they finally settle. On the other hand, an overdamped system is like a luxury car's soft suspension. It absorbs all the little bumps, giving you a smooth, slow, gradual adjustment to the big ones. And each of these damping styles has its own strategy, right? If you're an inventory manager who needs to react lightning fast and you've got the warehouse space to handle some overshoot, underdamped is for you. Critically damped is the gold standard of efficiency, the fastest way to get to your target with zero overshoot. Think of a perfectly engineered door closer. And overdamped? Well, that's for when a quick initial reaction is more important than anything else, even if it takes you longer to get all the way to your final target. Okay, now for the grand finale. Let's take this powerful second-order model and use it to solve a real-world puzzle that has frankly baffled economists using simpler models for years, the futures market. First, we got to get a couple of terms straight. A futures market is in contango when the price for getting something delivered in the future is higher than the price for getting it right now. And that makes sense, right? It costs money to store stuff, that's the cost of carry, so you'd expect to pay a little more for it later on. But then, sometimes things get weird. The market flips into backwardation. And that's when the future price is actually lower than the spot price. This happens when inventories are super low and people are desperate to get that thing right now, making it way more valuable today than it's expected to be in the future. So here it is. Here's the puzzle. Why does the market do this? Why does it invert and flip-flop back and forth between contango and backwardation? Your standard first-order models, they can describe each state individually, but they have no good explanation for the dynamic switching between them. Before our second-order system, this isn't a puzzle at all. In fact, it's the most natural, predictable behavior in the world for any system that has a spring and a damper. The market isn't randomly flipping out, it's simply oscillating. It's behaving exactly like a mass on a spring. Just look at this. The market's inversion is just a sine wave. The peaks, where the price overshoots into a premium, that's contango. The troughs, where it swings down into a discount, that's backwardation. It's this elegant, predictable cycle that's been hiding in plain sight the whole time. So what's the big takeaway here? What does all this actually mean? Well, it means we have this incredibly powerful new lens for looking at the economy, one that's grounded not just in abstract theory, but in the fundamental laws of motion that govern the universe. So let's just recap the biggest points. We've seen that economic markets can and do behave like physical systems. We learned that by adding just one element, inventory, our spring, you naturally get cycles and oscillations. And this simple change turns something that seems really complex, like the futures market inversion, into a totally predictable wave. And it gives us real math for ideas that used to be just observations, like price rigidity. But maybe the most profound takeaway is this. What we so often write off as irrational human behavior, market panics or speculative bubbles, it might not be irrational at all. It could just be a complex system doing exactly what the laws of physics say it should do. And that leaves us with one final big question to think about. If something as confusing as the futures market inversion is really just a simple oscillation, what other so-called irrational market behaviors are actually just physics in disguise?